What is a line integral, and why should I parameterize it?
Vectors! Vectors everywhere!
A line integral is a multivariable integration along a given curve in 2D or 3D space. Parameterization allows us to reduce the integration to a single integral.
Line integrals can be used to find the work along a given path, determine the mass of a wire, or determine the strength of the magnetic field around a conductor.
Basic shapes to parameterize include circles, ellipses, and lines. I'm the Batman.
And curves. The first step in computing a line integral by parameterization is to parameterize the path in terms of a vector with a single variable, r of t.
Given the function in terms of a vector, simply take the first derivative of r of t and then dot it with f of r of t. And now, this.
Okay, so we're going to solve this problem. Find the work done by the force field f of xy equals 0, x over the first quarter of a circle of radius 1 in the positive direction. So first, this is a work problem, which means we're going to use a line integral. So the definition of work is work equals the integral on your path of f dot dr. So we're going to go ahead and solve this by parameterization of path. So the first thing we want to do is draw a sketch of our path. So we know we have a circle. Let's draw that a little bit bigger. We have a circle here of radius 1, and it's the first quarter, so we're going to go from 0 to pi over 2. And we're going in the positive direction, which means counterclockwise. So this is our path for integration. Now what we want to do is represent this with the parametric function r of t. By the way, the circle is c, that's c. So we're going to write r of t equals, the parameterization of a circle is cosine of t, sine of t. And this is from 0 to pi over 2. So this is our parametric function. So next, we're going to want to find dr. Now dr is the same as r prime of t, which equals, we just take the derivative of r of t. So that's going to be negative sine of t, cosine of t, cosine of t. All right, that is r. That is r of t, r prime of t. Now, we have our force field in terms of x and y, but we have our dr in terms of t. So we're going to have to do something about that. So instead of writing f of x comma y, we're going to do f of r of t. So f, instead of x and y, we're going to use this x and this y. So it's going to be f of cosine of t sine of t equals 0. And instead of x, we're going to use cosine of t, which is the x component of r of t. Now, this is a dot product. So in order to find the work, we're going to have to take the dot product of f and dr. So let's rewrite this integral. Work equals the integral of f, which is 0, comma cosine of t, dotted with dr, which is negative sine of t, cosine of t, dt. Now, to take this dot product, it's this times this plus this times this. You should all know how to take the dot product. So we're left with work equals the integral. Now we have limits from 0 to pi over 2 of 0 times negative sign is 0. So we have 0 plus cosine squared of t dt. Now this integral is very solvable. You're going to do some calc 2 and get pi over 4. And that's how you solve a line integral by parameterization. A real-world use of line integration is Ampere's law, which states that for any closed-loop path, the sum of length elements times the magnetic field in the same direction is equal to the permeability times the electric current enclosed in the loop, or simply this.
Using the variables from the figure in the last slide, the enclosed current is simply the initial current times the sum of the circumference squared minus the inner radius squared, okay, all over the circumference squared minus the middle radius squared. B is the magnetic field strength and is usually a constant. ds is the change in circumference. Since the cable is a cylinder, this area is given by the function we all know and love, 2 pi r. Therefore, the integration becomes the formula that is listed on screen.